All right, we're on to section 5.4, the companion to 5.2. And looking through this section, there are a lot of similarities to 5.2 that we've already talked about with respect to independence and bases. This one is going to connect some of the stuff that we've talked about with in regards to column space and null space, with the bases and everything that we talked about in 5.2. So I've tried to cut this down. We're going to do about 4 problems out of this section just so that you have some good examples to work from as you do your homework. And our first one here, we have a matrix A and we want to find bases for the row space and column space. Remember that the row space will live in Rm and the column space will live in Rn. So those are, two subspaces of two different overall spaces. Now, practically, it looks very similar. We could do some row operations on this matrix and get down here to its echelon form. We see that it has a rank of 2. Actually, just using the 2 top vectors here in the echelon form works for providing a basis for the row space of this matrix. When you do row operations on a matrix, it does not change the row space overall. So yeah, we still have a 2-dimensional row space, and those are a good basis. Now, the overall rank of this matrix is 2, and that means that our column space is going to be of dimension 2 as well. But I hope that you can see that these first 2 columns are not going to be a very good choice for a basis for the column space. They don't have anything in their, third and fourth components. Whereas all of the vectors up here, do something to the third component or the fourth component or both. And so what you end up having to do here is, yes, you choose which columns to look at based on which columns have pivots. And, here we have 2 ones. But yeah, to pick the candidates for the column space, you actually go back to the original matrix. And these 2 columns up here form a basis for the column space. So yeah, row reducing and then interpreting that row reduced augmented matrix. Okay, not so bad for that problem. Next, we're going to look at a problem that's pretty similar, except we're just going to be finding different bases. Trust me that this stuff is stuff that I've already mentioned to some extent. It's just it's rephrased in this section. Here we go. Now, for this matrix A, we're going to find bases for the null space and the image of A, which, again, is just another way of saying the column space here. Yeah. So here we go. This one's just a little bit different because we're finding the null space now. So again, we would set up this homogeneous, system here where we've got 0 on the right-hand side, the 0 vector on the right-hand side. We would row reduce and put our solution into parametric vector form. Right here. We see that we're using 2 parameters because we have 2 free variables. And each of the vectors associated with those, parameters are going to give us a basis vector for our null space. So here we go. We have our two null space vectors coming up here first. Jeez. Here we go. This vector corresponds to the parameter s. This vector corresponds to the parameter t. And then these other two vectors that are in the image of A, just like the last problem, what we do is we see that we have two pivots in the first two columns of our row-reduced matrix, and we go back to our original matrix and choose those corresponding columns for the basis of our column space. So we have a two-dimensional null space and a two-dimensional column space here. Geometrically, what this would look like is this is a transformation on four-dimensional space onto four-dimensional space because we have a 4x4 matrix initially. When it says that we have a two-dimensional null space, that means that we have two dimensions of squishiness. So that means that while the space starts out four-dimensional, we squish everything onto two dimensions, and the null space represents the space that has been squished, and this represents the two dimensions that we have left. Cool. All right, moving on. A couple questions like this. Can a 5x6 matrix have independent columns, independent rows? Justify your answer. Okay. So let's go ahead and take a look at the columns first. This is a 5x6 matrix, so we've got 5 rows and 6 columns. Let's go ahead, since we want to have things that are independent, let's go ahead and throw some pivots in here. You know, as I'm putting squares around this, imagine that these things are becoming pivots, so they're leading ones, and everything underneath them is becoming 0. So, as we can see here, the most pivots that we can have in this context is 5. We can only have as many pivots as our smallest dimension. And in this case, if we were looking at all of the rows as their own column vector, if we were looking at all of the columns as each their own column vector, we could see that the first 5 column vectors could be independent, but the 6th vector really has nowhere to go. We're already spanning a 5-dimensional space there, and these vectors are all elements of R5, right? Because they're 5 components long. And so this last one necessarily makes all of the columns dependent. So, nope to that question. If we look at the rows, however, we do have a pivot in each row. And since those are working in a 6-dimensional space and we have 5 vectors, those 5 vectors would span a 5-dimensional subspace of 6-dimensional space. So rows span 5D subspace of R6. And that's cool. So, yes, we can have independent rows. Okay, I like those kind of questions. Good, good, good. Cool. All right, we're going to keep going. Keep going. Here we go. Now we have a 5 by 9 matrix. Is it possible that the dimension of the null space is 3? Justify your answer. And you see, I've already written here what this might look like in a matrix equation. We'd have a 5 by 9 matrix A times a 9 by 1 vector X that gets mapped onto a 5 by 1 vector B. That means that A is a linear transformation from R9 onto R5. So we're moving from a 9-dimensional space onto a 5-dimensional space. Now that kind of linear transformation necessarily has some squishiness to it, right? We're starting off with 9 and then getting squashed down onto some subset of a 5-dimensional space. And in this, we have to have at least 4 dimensions of squish. And so answering the question, is it possible to have the dimension of the null space equal 3? Nope. We need at least 4 dimensions of squish. We would have 4 dimensions of squish if we mapped all of R9 onto all of R5. But, if we were to, make this into an augmented matrix and get down to the place where, we're solving for, the null space, right? So on the right-hand side, it's going to be a bunch of zeros for, the zero vector. But anyways, well, here, I should think about this. I drew too many zeros. Let's make this a little bit real to life. If we've got 5 rows, we should have 5 zeros. But it's certainly possible that, after row reducing, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's certainly possible to have a row of all zeros at the end after doing some row reduction, which would mean that we would have, let's say 4 pivots somewhere along the way here in the first 4 rows. And if that happened, we would be transforming all of 9-dimensional space onto a 4-dimensional subset of 5-dimensional space. And in this case, so what I just said is here we'd be taking R9 and transforming it onto, a 4D subspace of R5. And if we're doing that, then we'd have 5 dimensions of squish, right? And it could theoretically get as bad as if we are transforming 9-dimensional space onto 5-dimensional space, or some subset of 5-dimensional space. Let's say we squash everything to the 0 vector. This would be a very boring matrix. It'd be, 0 matrix. But in theory, you could take all of 9 dimensions and squash them onto the 0 vector in 5-dimensional space, and that would require 9 dimensions worth of squishiness. So you would have a 9-dimensional null space there. Hopefully that made a little bit of sense. We can click through the explanation that they have here for a little bit. yeah, they're using the rank theorem here to show that, yes, the dimension of the null space plus the rank should, be equal to n, the dimension of Rn. And so, yeah, they're saying the same thing, that the null space would need to at least be 4-dimensional. Okay, keep going. I guess this is kind of the ending of this section, where we're going to look over a couple of just the following are equivalent theorems, just to make some more connections between the different ideas in linear algebra. So the first one, we have an m by n matrix. The rank of A is equal to n, so it has full column rank. Or is that full row rank? Good grief. When I'm just dealing with letters and I don't see something, it's confusing. All right, well, it has at least full something rank. I'll figure it out soon. They're saying here that the row space would be equal to Rn, so that the rows of A span Rn. That makes sense. Okay, in order to have the rank equal n, are we going to be working with a matrix that is tall and skinny or short and wide? Let's think about this. M by n, and we want... All right, so this one would be something like 4 by 2, and this would be something like 2 by 5. If we want to have a hope of having full n rank, and I guess it is column rank. Okay, I said the right thing initially. Here we could have 2 pivots in a 4 by 2 matrix and have full column rank. Here, in the setting of a 2 by 5 matrix, we could not have full column rank because we got too many columns. Okay, so we are in this scenario here. We have the rank of our matrix equal to n, the number of columns that we have. So yeah, full column rank. Okay, so the rows of A span Rn. Rn is R2 in this case, and yes, the rows would span. Sure. All right, let's keep going. No, oh, it's gonna leave. Oh, it's gonna leave. That's okay. We're gonna keep going. But just know that yes, we could be working with a square matrix here. M could equal n, but if we're not, then it is a tall and skinny matrix versus a short and wide matrix. The columns of A are independent in Rm. Indeed they are. Those columns would be independent because each one has a pivot. The matrix A transpose A would be invertible. That's cool. A transpose A would be an n by n matrix, so it would be a 2 by 2 matrix if we multiplied, say this matrix times its transpose in that way. There exists an n by m matrix C such that C times A is the identity. So that means that there's some matrix C that kind of acts like an inverse when you multiply A on the left by C. That's cool. And if ax equals 0 for some x in Rn, then, okay, x is the 0 vector. All that means is that we have a zero-dimensional null space here. Zero-dimensional null space. Cool. All right, so that's what it looks like to have full column rank. All of those conditions happen at exactly the same time. Now we're going to look at another n by n matrix. This time we're going to have full row rank. So we're going to be in the situation where our matrix is short and wide to some extent. So in this case, our rank would be equal to m so we've got full row rank. That is equivalent to saying that the columns of A span Rm. So again, in this context, I put two pivots there. So the columns here would span R2. Wonderful. The rows of A are independent in Rn. Indeed, there would be two rows that are independent from one another. The m by m matrix, AA transpose, would be invertible. There exists an m by m matrix. When you multiply on the right by this matrix C, you could get the identity matrix. And this system, AX equals B is consistent for every B. So that's really saying the same thing as number 2 is the easiest connection to make for me, is that the columns of A span Rm. That means that that system would be consistent. We could find a solution every time for that system, AX equals B. And that's really the end of it for this. Do notice that we just talked about the cases where we have full column rank, and then we talked about the situations where we have full row rank. When you have an n by n matrix, a square matrix, that has full rank total, all of those conditions are true at the same time. So you've got lots of independence everywhere, column independence, row independence. A transpose A is invertible, AA transpose is invertible. All of those nice qualities are sustained in one nice square matrix. All right, so I was trying to make this short. I will see you in the next one. This has been section 5.4. Now you should be ready and raring to go for homework number 17. All right, I'll see you in the next one.